So I'm Lorraine, and Jeremy gave me this title, History of Atmospheric Science from Satellites. And I kept thinking about the title, and I had like a picture in my mind, and the problem is the picture in my mind is not atmospheric science, but it's a very narrow piece of it. So I'm going to go through a long introduction. I'm going to talk about everything, because every time I wanted to say something about the things I wanted to teach, I've realized I had to go back a step and do something in the introduction. And then I'll talk about Earth observations from the very beginning, because at the very beginning of Earth observations from satellite, it was all about atmospheric science. It was like they had this technology, and I work with engineers, so I know how they are. We can do this great stuff. Find me a scientific application, please. And so it was kind of like that in the beginning also. We have this great stuff, we're going to do satellites, but then please give me a reason for doing it. And it was atmospheric science from the beginning. And then go through the past, and I don't have as nice stuff as Jeremy has. I have no pictures of sharks. I have nothing like that. So it's going to be much more, I don't know, less movement probably. So we're going to talk about the atmosphere and what is in the atmosphere. And I have a picture here. This is from the International Space Station. So you get a certain perspective. And we can see here a lot. Now, if you notice where the yellow arrow is pointing, that very thin blue stuff, that's the atmosphere. So it's very thin. And like, people don't think about it because we live at the bottom of it, and it seems like it has a lot of space. But I could get into a car and drive to the top of the atmosphere in an hour. It's really not that far away. So it's a lot more spread out and very, very thin. But what do we see in the atmosphere? What is the atmosphere made of? And you're supposed to answer this question. Okay, so I heard molecules. Molecules are gases. Yes, there's a lot of gas molecules making up the atmosphere. Gases is one of them. Anything else?
Water vapor.
Water vapor is another gas. That's a very important gas. Dust. Smoke. We see smoke here. There's a fire burning. I never have anything, but you can see there's a fire plume there. That's smoke. These are particles. What about all the white stuff? Clouds. There's clouds in the atmosphere. The major part of the atmosphere are clouds. So we have gases, including trace gases like water vapor. We have smoke and dust. These are called aerosols. We have clouds. Clouds are made of droplets, water droplets, and water ice. And finally, we have precipitation, like rain and snow that falls down, right? So there's a lot in the atmosphere. And I included some more gases here. Nitrogen and oxygen are the main gases in the atmosphere. Water vapor, and then also the trace gases, like the greenhouse gases. I mean, that's a newsworthy thing now. So clouds, precipitation, and aerosols. Okay? So we can see them now in this picture. We can look at that thin blue line that's the atmosphere, and that's the gases scattering light back to the International Space Station. We see clouds, we see smoke, aerosol, and this may be dust right there that I'm not really sure, right there. And why should I care about these things? Why do I care about gases? Why do I care about gases in the atmosphere? They scatter. Greenhouse gases, right? That keeps the planet warm. We're breathing. We all like to breathe, right? And I don't care what Jeremy said about if we like to breathe, we like phytoplankton. If you like to breathe, you like the atmosphere. Okay, so I heard something else over here. I didn't catch it. They absorb. That would be the greenhouse gases absorbing radiation, keeping the planet warm. What about clouds? Why do we like clouds? What do we care?
For the water cycle?
The water cycle is really important. That's clouds and precipitation, and gases like water vapor. So where this precipitation goes has to do with the clouds. The clouds are also radiatively important. They reflect a lot of sunlight back to space. They also act sometimes to keep the planet warm. What do we care about aerosols? Nutrient cycles, that's very good. They're also radiatively active. So in some ways, and I don't have any of this to show you, but in North America and in most of Europe, we're reducing our particulate pollution. We're reducing the amount of aerosols in the atmosphere. It's going down. Skies are blue here now in the summer. When I came here in the 90s, it was white. There was no blue sky. So we're killing our particles. We're killing every last particle in North America. And the result is we're changing the energy balance, and we were offsetting greenhouse gas warming. So the cooling that the aerosols were giving us is disappearing. Planet's getting warmer faster. Keep that one in mind, huh? Aerosols are also really important in the water cycle because they act as cloud condensation nuclei. The water condenses around the aerosol particle. So there's a lot of people interested in all this and in weather in general. Weather is really important. People care about the weather a lot. And so all these pieces kind of go together to become the weather. And like even gases, nitrogen and the oxygen in the atmosphere, creating the atmosphere, knowing what the temperature is really important to predicting the weather. So now I want to talk about measuring these atmospheric parameters. We've seen this. This is the Keller Curve, right? At Mauna Loa. We know that from 1960 to 2020, it's been going up. The amount of CO2 has been going up, measuring CO2. How is this measured? By a flask. Going to Mauna Loa, opening up the flask, collecting air, closing it, taking it down back to Scripps, and doing the analysis. This is the Keeling curve. I happen to have been at Scripps as a student when Charles David Keeling was starting it. I have this 1980 there. That's when I was at Scripps. And in my modeling at the time, we were using 340 parts per million in our models. And look where it is today. But it's all done with flasks. It's all done in situ. No satellites. Here's in situ cloud measurements. For example, using a balloon. These are all ice crystal pictures. The old stuff, some high definition stuff. So you can fly a balloon, you can fly aircraft through a cloud, and you can measure the in situ properties of the cloud. Or how about measuring rain from in situ precipitation measurements, right? Rain comes down, and you can measure it falling and how much mass hits the plate and how fast it's falling through the lasers that are pointing at it. So that's all done in situ, right? You don't need satellites to make measurements, but satellites give you a different perspective. And here are some in situ aerosol measurements. There's different devices. One's a nephelometer that draws air in through the tube and then shoots lights at it and measures the scattering inside the tube, or collects the particles on filters, and you take it back to the lab and you analyze the chemistry from the filters. And you can break down very clearly what kinds of aerosols on different days from the filters. So these are all in situ measurements. And there's nothing wrong with in situ measurements, but they all are very local. And the question is, if you have a question like, how much aerosol is in that smoke plume that we're seeing the whole plume? So I asked this question to a group of Cub Scouts. They were 9 and 10-year-old boys. I was doing a gig, and they were at Goddard. And so I asked them, how do I measure how much smoke is in that plume? And Danny Bickford said, well, I'd measure it. Okay, so what do you mean by measure it? Oh, I'd get into an airplane, and I would fly how long along it and across it, and he's 9 years old. And then I would know how much smoke I had. So I figured he'd take the concentration that he measured, and he would tell me how much smoke. But I said, what if you don't want to get into the airplane? What if you don't want to measure in situ? What if you want to sit in the comfort of your home and measure it? How else could I measure the smoke plume? And there was another Daniel there, Daniil. And Daniil said, I can't believe that he said this. He was 9 years old. He said, you know, at night at the campfire, when I shine my flashlight at the smoke, really bright. He said, is there some way we could tell how much smoke it is by using the flashlight? Kid's a genius, you know. And yeah, so that's kind of the remote sensing piece of it. So remote sensing is when we're not going to actually sample the substance. And it's usually the interaction of the substance with either light or sound. That's the remote sensing piece of it. And so the more smoke, the more light scattered back. And Daniil had the whole story right there. So now we talk about, you know, these suspended particles in the atmosphere that we want to measure, the clouds and the precipitation and the aerosol and the gases. Well, how do we do that? How do we translate the amount of light to the properties we want? And for example, here's smoke. You can have black smoke or you could have white smoke. So these particles in the atmosphere, and I'm going to use particles for gases also for a while, they both scatter and absorb light. So you have to take into account that it can be white or it can be black smoke. And that's the relative amount, how much light is scattered back versus how much is absorbed, whether the smoke is black or white. Okay? And so, and you're going to go into a lot more of this afternoon and even get some equations. I have no equations. But the idea is that incident light, if in a particle and it's completely absorbed, it's just, right, that becomes black. That's a black particle. But sometimes, can you guys see the little blue arrows? It's a little fading here. The light isn't completely absorbed. It scatters in all directions around that particle. And it scatters at different amounts in different directions. So that's the phase function. So, you know, most of the light might be scattered forward, and some side scattering and some scattered back. So there's a directionality to this event when light hits the particle. And it depends what the wavelength is. Because you'll have different phase functions depending on the wavelength of the light that hits the particle. So how much is absorbed, how much is scattered, what's the directionality of the scattering, what's the wavelength dependence, the spectral dependence. These are all the signals that we're dealing with when we do remote sensing, when we are looking at the interaction between the light and the particle. And it's from that information that we do remote sensing. And, gosh, this is kind of strange. Okay, so plot here showing two wavelengths. The wavelengths are the same wavelength, but the particles are different sizes. And there is it matters, size matters. So you're going to get a different scattering signature for the same wavelength depending on the size of the particle that is involved. And there's an analogy between the same size wavelength and different size particles, same size particle and different wavelengths, different colors, It's all related, and it's all related to this parameter here, which is 2 pi r over the wavelength. So the point being is when when the radius of the particle, the size of the particle, and the size of the light wavelength hitting the particle are about the same, it's when you have the most scattering. And these are for spherical particles, and you know, it's a lot of simplification here. But the reality is, this is the same scene looking at it on the left in visible wavelengths, and on the right with longer wavelengths in the shortwave infrared. And I'm looking at smoke plumes off the coast of Australia. That's Australia there. So on the left, it's our visible, we see it, we see the smoke plumes, right? Everyone sees the smoke plumes. Okay, but on the right, we kind of see brown spots where the fires are. You see a hint of something, right? But you don't see smoke plumes. Where did the smoke go? Right? Where did it go? Well, we don't see it because we're shining light the wavelengths are too long. And they go right through the smoke and right back, and they never get affected. They never get scattered in the same way. So there's this real interplay between size and wavelength in remote sensing of atmospheric parameters. And I just want to give you a little idea about the relative sizes of these things. That little speck, that's an aerosol. And then you get cloud droplets like the two circles. And the cloud droplets can grow and grow and grow. But a typical raindrop, you see this huge sucker, right? At the bottom. So there's a lot of order of magnitude in sizes of these things. And if we want to look at gas molecules, they're even, orders of magnitude smaller than the aerosol. So there's a wide range of sizes in the atmosphere. But luckily, we have a wide range of wavelengths to work with. And we can use the entire electromagnetic spectrum to look at things from the aerosol sizes, which are like at the visible light, through the infrared, which would be good for getting cloud droplets, all the way out to radar, where the clouds will become invisible, just like the smoke was invisible to the shortwave infrared. Go out longer to microwaves and radar, the clouds become invisible, and you're looking only at those gigantic precipitation particles, right? So we have a lot of tools to use for the electromagnetic spectrum. So for remote sensing of aerosols, we'll use scattering from the UV, the visible, and the shortwave infrared, because that's what's sensitive to their scattering. For the clouds, we'll go into the thermal infrared. And for precipitation, we can use scattering from radar and microwave. So when you're talking about remote sensing of atmospheric science, it involves the whole electromagnetic spectrum, because the particles are so many different sizes. And there's also absorption. And absorption is also spectrally dependent in an even bigger way. So here we are along the electromagnetic spectrum again. And there's places where we have atmospheric windows where you can see through the atmosphere to the ground, but other places where it's not. And so using the absorption properties in a smart way, you can learn a lot of other things, especially about trace gases, because there are certain places that are, for example, carbon dioxide. Certain places where the carbon dioxide is absorbing a lot. So you can look there to see how much carbon dioxide there is. And there's a couple of things. One is temperature profile. I'm not going to do this. Okay. So that's the end of the introduction. So there's scattering, there's absorption. We use both of those. Absorption is very good for gases, but for other things also. Scattering is this interplay between the size of the wavelength and the size of the particle. That's all the atmospheric science, and it's all remote sensing. Questions? Very long introduction. Okay, now I'm going to talk about the very beginning of satellite Earth observations and tell you that it was all atmospheric science at the beginning. What was the first satellite in space? Sputnik. 1957, October 1957. What was the first US satellite in space? Ooh. What? Not yet. It was one before Tyros. It was Explorer 1. Only 3 months later. Only 3 months later. Okay. What did Explorer 1 do? Okay, Sputnik beeped. Sputnik went beep, beep, beep. That's all Sputnik did. What did Explorer 1 do? 3 months later, we have an improvement in technology. It carried cosmic ray detectors and discovered the Van Allen belt of charged particles way up high. So it actually did something. It did. Okay, and what was the first US Earth imaging satellite? And that was Tyros. Oh, no, Vanguard. But it had technical issues and returned and no data. What was the first successful Earth imaging satellite? That was Tyros, and that was 1960. So there's not a lot of time between Sputnik and our first Earth imaging satellite, right? And Tyros had television in its name, because what Tyros did was carry television cameras and pointed them at Earth. So they had this technology, they knew they wanted to do something with it, and they thought that the best application for an Earth-observing satellite would be weather. And the thought was, well, we could watch a hurricane before it hit shore in a way we couldn't watch it any other way. And that was kind of the motivation for turning the television cameras down and taking pictures of Earth. So this was Tyros, and this was the kind of imagery that it sent back. Really, there was no high-definition television back then. It was very fuzzy pictures. And the idea was to help meteorology, hurricane tracking, things like that. Now, what was interesting about Tyros, was in 1991, I had a chance I had first come to Goddard, fresh with my PhD, and we were doing a remote sensing project using film cameras. Film. You guys ever seen film? Okay, and film cameras. So we had 4 Hasselblad cameras. They're 70 millimeter images. We were pointing them down from the back of an airplane, taking pictures as we flew. We had gelatin filters in front of each one, and that kind of gave us different wavelengths from the Hasselblads. And we would take the film, develop the film, go into a lab and digitize the film with a light. Okay? Then we would take it all to a lab, and we would run exposed grayscale calibration things and run it through the processing so we could calibrate the radiance that hit the film and get a radiance number of the ground surface. Anyway, had us working with this guy on the right. His name is Bill Lazenby. He was a photographer. He took pictures. And he worked at Wallops, NASA Wallops, down on the eastern shore. That's where a lot of the satellite transmission comes down through the receiving station at Wallops. And Tyros was being beamed down to Wallops. The television signal was being beamed down to Wallops. And it was television. It wasn't like computers. So it was there on the screen, and then it was gone. So the first one, they weren't set up to record it. Bill's job was to sit there with a film camera in front of the television screen, taking pictures. So they had a record that could become that image that we see there. And then eventually, they got figured out they better save these images, right? So they worked on it. So anyway, that's Bill. He's standing with Yoram Kaufman, who was my mentor at Goddard when I first came. And we'll talk about Yoram later. But I always found this fascinating when Bill told me this story, that he had to take pictures of Tyros. So there's a weather satellite era from 1964 after Tyros, which was very experimental, to 2000. And Nimbus was a series of 7 satellites that carried up to 33 sensors altogether. And it was really did a lot of different things. It provided images of Earth for 30 years, the Nimbus program. It had ozone mappers to map gases. It had thermal infrared radiometers for clouds. It had microwave radiometers for precipitation. And then it did have the CZCS, which Jeremy talked about, but we're not talking about it. He had one ocean color instrument. But mostly it was for atmospheric weather. So here are some of the Nimbus results. Thermal infrared imaging, the hurricane I told you, for weather, and the ozone hole. The ozone hole was a Nimbus result. And so initially, one of the major things it did measure was ocean and air temperatures, air pressure and cloudiness. All would get fed into forecast models for weather forecasting. We had profiles of temperature through the atmosphere, and I don't want to go into how that's done, but that was a major product for helping weather forecasting. And we had microwaves that could see through clouds and profile temperatures inside hurricanes. Again, from Nimbus. You couldn't do this stuff in situ. And it made a huge difference in forecast skill. Because suddenly, we had temperature profile and water vapor profile across the oceans where there was no data before. So you could input this into your forecast model, crank through your equations to get to what the weather would be like tomorrow. And it made a huge difference to be able to initialize across the globe using temperature profiles that you could only get from radio sounds on land. It carried a radiation budget at the top of the atmosphere to know how much radiation was coming in and how much radiation was going out. This was the beginning of climate measurements. And it was very big on stratospheric aerosols and temperature measurements in the stratosphere. And that's when they looked at the sunset and sunrise through that thin blue layer of atmosphere. And they could start to look at stratospheric properties. Okay, there were other weather satellites besides Nimbus. Geostationary gave us movies. And if you look at here, there was the experimental one in 1974, but the operational one goes in 1975 to the present. I was in high school in 1975. And so when I finally got to school and I got into my first atmospheric science courses and we were starting to learn how to forecast weather, this technology was still new to be able to see the movement of the clouds in real time from satellite. Okay, it just, what it gave, the ammunition it gave to a weather forecaster was amazing. And then there was a Noaa series of polar orbiting satellites carrying, and you have to love this name, a very high resolution radiometer. It's AVHRR. And it spanned a long time. And it was a finer resolution, 1 kilometer versus 8. Nimbus had been 8. So when I came To start aerosol remote sensing, it was AVHR that I was working with. So the summary of this part was, this is the weather period. And these were workhorse operational weather satellites by the time at the end of this period. And people were depending on them now. It improved the weather forecasting a lot, provided cloud images, cloud top temperature, temperature profiles, water vapor, Earth's energy budget, stratospheric. And they were pioneering aerosol retrievals from AVHR, only over ocean. And TOMS, they had a very coarse spectral resolution. TOMS was the ozone measurement instrument. And as a byproduct, they discovered they had an aerosol signal in their data by accident. And it became an important aerosol contribution over time. Okay, any questions on the weather satellite period? Okay.
You used terminology in the fourth period. I tried to read online when I still don't fully get it. What does geostationary mean?
Good question. Very good. Geostationary means that it is orbiting at the same.
I have a video actually, if it helps at some point.
We'll show it later.
Yeah,
Okay, we'll show it later.
Yeah.
It means, in essence, that it's not moving in relationship to the surface underneath. So the polar orbiting satellites are going around the Earth, and the Earth is turning underneath them. So they're going to image. They always seem to be moving. And you could look at them in the night sky, and you can see them move, right? But the geostationary means it's just plopped over the equator someplace. And the Earth doesn't turn. The Earth it rotates with the Earth. So it doesn't turn. The Earth is not moving underneath it. Sun's moving, right? It's moving with relation to the sun, but not to the Earth.
Does it then only monitor that part that's underneath it?
Yes. And it's pretty broad. It gets a full disk, but it doesn't hit the poles very well. But it never leaves this place where it is.
There's a big difference in the distance. Geostationary orbits, to get that thing where you're just tracking around with the Earth, you have to do that 36,000 kilometers from the Earth. Whereas the polar orbiting ones are somewhere between 400 and 800 kilometers roughly. So it's, when Lorraine was pointing out about the spatial resolution that you could get with AVHR being 1 kilometer, it's obviously a lot easier to do that if you're only 700 kilometers from the Earth versus 36,000 kilometers. So it makes a big difference in what you can do with your imagery. And geostationary satellites this day still have a much coarser resolution than you can get with the low Earth orbit.
Yeah, but since it's sitting there, you can see the clouds moving. Right? I went to get a movie picture, but I was doing this last night, and it wasn't going to happen. So I'm sorry. That was a good question. Okay, this is some examples of this era. This on the left is what we're looking at here is a time from 1985 to 1999 over here. And this one is from 1989 to 1994. And we're looking at different, this is aerosol extinction. And this is aerosol optical thickness. They're both measures of aerosol extinction. And what we're looking at in 1989 is Pinatubo. Big volcanic eruption, put a lot of particles in the stratosphere. And so these are stratospheric measurements here on the left. And this is total column aerosol optical depth looking down. You can see. So this is kind of what we were able to do with the weather satellites. Okay. Now we enter a new era. And this is where we're going to move from weather to climate variables. And this is the Earth Observing System, or EOS. And it starts in the year 2000. Terra is launched at the end of 1999 in December. After commissioning and checkout, we start to get data from Terra. In 2000, it's carrying MODIS, it's carrying MISR, it's carrying Ceres. 2 years later, its twin goes up, Aqua. It's carrying MODIS and Ceres and a bunch of atmospheric profilers. Aura's 2 years after that. That's the chemistry mission. Ozone monitoring instruments focused on gases. Also in 2004, a few months later, we end up with POLDAIR, which is a multi-angle polarimeter. And then in 2006, we get our active sensors, CloudSat and Calypso. And we're kind of moving from weather to climate. What do I mean? So before the EOS satellites, we were offering users radiances, reflectances, temperatures, and they were calibrated in georeference if you were lucky, not always. But we weren't offering like products like what you're used to today. They were not really products till much later. And the EOS satellites were using validated geophysical products, ocean color, aerosol optical depth. So it's a different mindset now. So here are some MODIS cloud products using the infrared channels. There's a whole lot. I pulled out a few. These are nighttime pictures of cloud temperature on the upper left for liquid clouds, cloud fraction for liquid clouds, cloud fraction for ice, cloud height for ice. And you can get these global pictures, right? These global pictures of these products. Now the thing is, we had previously to MODIS, we did have cloud products that worked in the IR, or we had IR measurements that could be turned into products. But MODIS gave us a little bit better resolution, better calibration, and we started to produce products that the public could just pick up and use. This is just a few. There's a whole bunch of stuff that you could use with IR. But I put this in here because this all uses IR, and none of this has to do with PACE. PACE has no IR. So all these products that we're used to with MODIS will not be on the PACE. But we do have something that was used that will continue to PACE, and this is what we call cloud optical properties. It was new for MODIS because now we had the shortwave infrared and the cloud optical thickness, cloud droplet effective radius. And the way this works is if you use a shortwave infrared channel and a visible channel, and you calculate for a specific geometry, it has to be a specific geometry, what type of cloud, what the size of the droplets in the cloud, and how optically thick the cloud is, you can calculate that theoretically and find out what would we measure at top of atmosphere given a certain type of cloud for a certain geometry. Okay, so if my cloud droplets were going up the right-hand side, let's say 16 micron droplets, it would follow that curve that says 16 microns along there all the way down. So it's pretty, so that would be its curve. If my optical thickness was 32, it would follow that 32 line upward like that. And then if you made measurements according to the 2.1 or the 0.75 reflection, you could find where in this lookup table you fell, and you could retrieve the size of the droplets and the optical thickness of the cloud. Yes.
That is over motion or over
Anywhere. Anywhere. There's different assumptions that go into the model depending on whether it's on what the surface underneath is. Yeah.
What is the cloud optical thickness?
Cloud optical thickness is an optical measurement of how thick the cloud is, how quickly it would be light extinguished as it went through. I'm not using a difference. I don't have a, I'm trying to like take one of these dots, that's a measurement, right? So that one dot would have a reflectance of 0.7 at 0.75. It might have a reflection of 0.3 at 2.1. So you go here, and it would fall on your lookup table at the intersection of a particular cloud optical thickness and radius. Okay, a little bit tricky there. But it was new, it was brand new for MODIS. We had done it with AVHRR, but it was really hard. And now this was a product that would just crank out and anybody could use it. And it was developed by Mike King and Terry Nakajima. And so you get these now global pictures of cloud optical thickness for liquid clouds, cloud effective radius for liquid clouds, and the same for ice. Global pictures of the droplet size in the clouds. This is brand new for MODIS, right? And now we've had it for 20 years. And something like this can continue with OCI, with PACE. Okay. So I'd come back to Yoram Kaufman and Didier Tanray. And they got together and they conceived and delivered the first MODIS aerosol product. They were good friends. Didier works in France. Yoram worked at Goddard. And this became, we were using aerosol we were using the visible and shortwave infrared from MODIS. And we could produce aerosol optical depth everywhere over land and water. And we couldn't do it over land before. And we could also get something called fine mode fraction. We could get a measure of the particle size for aerosol also because of this broad spectrum. So it produced aerosol optical depth or thickness, which is the optical measure of the aerosol loading, and the percentage of the total measured radiance attributed to smaller particles. So you could start to differentiate between dust, which is a big particle, and smoke, which is a small particle. And it had to do with that picture being able to see through smoke, because the particles are small. If you couldn't see through it, it would be dust. Okay, now, the original MODIS algorithm was a dark target algorithm. But we see deserts, we're retrieving over deserts also. And that was a contribution by Christina Shu here. And she came up with a deep blue algorithm. And there were different ways of parameterizing the land surface reflectance beneath the aerosol. So you could retrieve over land. And in both, you want the surface to be as dark as possible. And the surface gets darker as you move into the short wave. So deep blue used a wavelength that dark target did not and was able to retrieve over the deserts. And there's a third algorithm that Alexei produced. It's called Noaa. And he brought in a temporal factor. He said that the land scene is constant over 8 days. But the aerosol changes day to day. But in a reasonable box size, the aerosol is very homogeneous, but the land could have a lot of variability. And so with those assumptions, he was able to pull out more information, and he was able to do this at 1 kilometer, which was a finer resolution than we were able to do it over land. So there are three algorithms applied to MODIS for aerosol. See, what else was new for clouds and aerosols in the EOS era? Well, MISR was a brand new type of instrument. And it made use of the angular signal of the interaction between, in the scattering event. And from that angular information, we're able to do some typing of aerosol type, right? So the brown and orange and yellow colors are larger non-spherical particles, like dust. So you can see where the dust is. And that magenta color, that is a spherical absorbing particle. That would be smoke. And you can see that bright magenta color right there over Central Africa, where the biomass burning happens every year. So MISR gave us ability to learn more about the aerosol particles than just how much there is or their size. And it was Ralph Kahn who led that effort. What else is new for clouds and aerosols? Well, we went back to using the ozone measurement instrument, I guess. I always forget if it's measuring or monitoring. Ozone monitoring instrument. And here we're able to be sensitive not only to the amount of loading, but the amount of absorption the particles are, white smoke versus black smoke. This was a contribution that we could only do using the UV wavelengths, which MODIS didn't have and MISR did not have, but OMI did. So now all these different EOS contributions, right? The loading over land and ocean, the size of the particles, their absorption, their type. This was the contribution that the EOS sensors gave us. And this is my friend Omar. He was kind of the force behind this project. And what else is new for clouds and aerosols? The active sensors, the LiDAR and the radar. Vertical profiling through the atmosphere. And this has nothing to do with PACE either, but I wanted to be complete. But the most important contribution to the EOS era was not a satellite. It was AeroNet. And AeroNet is a network of autonomous instruments. There's sun sky photometers. In 2000, that's how they were distributed. Today, they're all over. If we're lucky, I can get to the roof tomorrow. I'll show you one in person. But they're very cute. They automatically wake up. They point to the sun. They measure the radiance from the sun. If it's the right time, then they'll measure the sky radiance all the way around. And from all that information, they'll be able to tell, you can invert that to get a lot of information about the particles. The size distribution of the particles, not just a fine mode fraction, but the size distribution. Single scattering albedo here is more absorption, spectral absorption. Because you have so much information now. You have all the angles from the scattering. You have the direct sun. We know how much radiation should be, the sun on top of atmosphere. So this is a sun photometer now. So it tells you how much makes it to the ground. It tells you how much is not there in the column. And this was under Brent Holman's guidance for 30 years, 20 years. Brent just retired last Friday. So that's all I'm going to say about the EOS era. That's where we are now. Modis is retiring, like Brent. Aeronet will continue, but Modis is going to be gone. Miser is going to be gone. OMI is going to be gone. We have continuation in Veers, okay? But PACE will be new. And PACE will do some of the things that we've expected from Modis. They'll do more than we expect from Modis. But there will be a shift. There's going to be a generational shift here. And I wanted to bring back all these people, because the thing I'm trying to say here is science is really important. But the science happened because there's people behind that. These are real people. I've had, I know these people. And a lot of them are retiring. DDA's retired. Brent's retired on Friday. Jorm passed away in a bicycle accident in 2006. And I think I'm still recovering, trying to recover from that. So these are real people. And they had their own quirks and their own strange ways of doing things. And I had cropped this picture before to take me out of it. But I was there. I was there through all of this stuff, right? I was there with Jorm and Brent doing field work. And that was before we had CMOS photometers for Aeronet. This was a hand thing, right? The beauty of the Aeronet stuff is that it wakes up on its own. This thing you had to move through its angles, right? So, the point I'm making here is there's a chain from Brent to me to you. And to summarize that, the satellite remote sensing began with the space race, but the first application was the need to observe the atmosphere. And don't let Jeremy tell you anything differently.
I didn't.
So it's rooted in the physics of the interaction between particles in the electromagnetic spectrum. And we moved from weather satellites to climate satellites. And from images and radiances to validated products. So this has been the progression. Some of the EOS era products can be continued with PACE, but not all of them. And aerosols will be the easiest to continue, and some of the cloud products. So when you say that there's an atmospheric component to PACE, it's a subset of what atmospheric science is, a small subset. And the important message, while we're rooted in physics, atmospheric remote sensing is all about the people, about building collaborative relationships and linking the chain from one generation to the next. And that's why we're here. Okay? We're going to keep this chain going. So that's it. Any more questions? Yeah.
So of course, measuring things with poles is a challenge, but I noticed on some of your aerosol retrieval maps, it appears that there's better coverage in the Arctic than the Antarctic. Why would that be?
Okay, because all three algorithms that we have now, dark target, deep blue, and Maya, they can't retrieve aerosol over snow. We can't characterize the snow well enough to get a quantitative retrieval of the aerosol above it. So in the Arctic, it melts. So there are a period of the year where we can actually retrieve up until the coastline. The Antarctic, we can't. Calypso, the LiDAR, will retrieve over anything because it brings its own light with it, its own source. Anything else? Anyway, I'm here all week. We can chat about anything. Okay, thanks. Thanks, Pingwong.